So thanks a lot for the invitation. Um, it's very nice to see some faces that I didn't see in a long time. So I would like to talk about some rather recent result on a free boundary problem, which is like a variation of a famous free boundary problem introduced by Alt and Caffarelli um, at the during the early 80s. So the problem is the following. One consider the functional given by the Dirichlet energy plus in a domain omega and the characteristic function of the positivity phase. And if you look at a minimizer, for instance, formally you get like the following free boundary problem. So you are harmonic where u is positive and in omega, and so the other phase is a zero, right? And you have a jump condition along the free boundary. Okay, so this is like assuming that everything is smooth here. Okay, that you have a jump of the normal derivative equal to 1. So the variational approach to this type of free boundary problem, so making like rigorous somehow this Euler-Lagrange equation, has been done in a very famous paper of Alt and Caffarelli in 82. And later, Caffarelli developed a viscosity approach to this type of problem, so not looking necessarily, not relying that much on variational, and actually in which viscosity sense one can get this type of equation. Okay. So there are, of course, it's a problem which has been generating a lot of works. This is because it's some sort of very easy to state, but as I hope it will become clear later, it has a very strong analogy somehow with the theory of minimal surfaces. So it's a very important problem. But for example, another one which is very famous is the obstacle problem. And in this case, the theory is much more developed. Actually, the one-phase problem, there are still many open questions. Okay, so when you look at this problem, natural generalization would be to put variable coefficients, right? Possibly a matrix or even a function, omega of x, or a matrix A of x. And there have been many works related to that. And so I quote some names here, but I'm missing a lot of people, of course. And it's very natural to look at a variable coefficient problem because for as a motivation, one could think about you look at the one-phase problem on a curved background, right? A manifold. And then, of course, when you write in coordinates, you will have coefficients appearing, right? So it's very natural to look at this type of model. So up to now, or at least up to relatively recently, the standard, the canonical assumption on omega of x or A of x, besides the regularity assumption, which is a very important problem, but the canonical assumption was uniform ellipticity. So in particular, omega of x, if you take the scalar case, the case of a function, is not vanishing, okay? So for some reason that I will explain later, it's nice to have a look at weights, functions, right? Or if you want to think about it like an isotropic media, where you allow the weight omega of x to vanish. So one class of weight which is very well suited for kind of variational problems because of the links with harmonic analysis are mooking up weights. So here this is like the definition of native weight omega. So these are like somehow like ways for which you have some control of the set where you are either singular, so plus infinity, or zero. Okay, the singular or degenerate set. So when you think about it, like like you have like just away from the set the set that I denoted lambda naught and lambda infinity, where the weight is either vanishing or blowing up, right? You of course, like you have like a uniformly elliptic problem, right, with coefficients, right? So you fall into like the previous works. The important thing is how the free boundary or the optimal regularity of the solution of my free boundary problem will behave close to close to the singular set. By singular set, I mean the set where, for example, omega vanishes or omega is plus infinity. Okay. So a typical example that one can have in mind is like you take like you are in Rn, right? You take like a finite number of variables, right? And you take a power alpha, which is well suited. Okay, so that like it's an A28. Okay, you could think also. And I will come back to that maybe later. You can think also about like you take like a submanifold, right, embedded in Rn, and you look at distance to this manifold to some power, okay, and it would be a nice weight also. So, well, this type of weights have been appearing recently in several results in higher codimension harmonic measure. I will come back to that. So somehow, like what we developed basically with Lambola and Teixeira is which type of optimal regularity at the moment. I mean, when you are like very close to the set where omega vanishes and omega is blowing up, right? So why do I talk about this kind of special structure? Well, because like if you look at an old book of Duvaux and Lyons, or Lyons and Magenes, they study like in the theory of semi-permeable membranes Alcafari type functionals of this type. So basically you are taking like think about for the first time beta equal to 0, okay? So in my notation here it's alpha equal to 1/2. So you take like a directly energy in a domain which is like in the half space, right? And on the piece, so imagine that you have a half ball, right? The domain omega is a half ball. And on the piece of the boundary where it's flat, so you are on Rn, right? If your half ball is in Rn plus 1 plus, you are penalizing where for the volume of the positivity set. Okay, so it's called like for beta equal to 1. This is a thin one-phase problem because instead of having the free boundary in the set omega, right? So here in Rn plus 1 plus, the free boundary lie in a codimension 1 set, which is here in the simplest geometry, the hyperplane Rn, right? Seen as the boundary of the half space. Okay? So, I mean, like if you know more about like the obstacle problem version of this problem for in the case of the obstacle is the famous Signorini problem, right? So actually, like if you write like kind of at least formally what means this problem, well, you have like since you are taking like an harmonic function inside the half space, right? So on the boundary, okay, when you restrict, it's going to be a function which is satisfying delta 1/2 of v equal to 0, where for alpha equal to 1/2. And actually, what you can prove, for example, by exhibiting like some kind of model solution, is that the growth that you have close to the free boundary is not Lipschitz, which is a case of Alt-Caffarelli, the standard case, but it's Hölder, and the power of the Hölder exponent is exactly the power of the Laplacian. Okay, so basically this whole model, and if you put a weight of the form modulus of y to the power of beta, so y is like the extended variable in the half space, right? You end up using the Caffarelli-Silvestri extension, or okay, whatever you call it. You end up like getting a model which is even written in this formulation here is intrinsically non-local, and taking a trace, okay, you have like fractional Laplacian of delta alpha v equal to 0, so v is a trace of u on the hyperplane Rn, and you grow, at least, I mean, you have to prove it, but formally, okay, you grow like power alpha, okay, away from the 0 set. Okay, so basically, so the thin one-phase problem, if you want, or like a generalized version of it with this weight beta, modulus of y to the power beta, appears as an Alt-Caffarelli problem, so a problem of this type, but for powers of the Laplacian, okay? And of course, like one can imagine many like versions or like variations of this type. So as I was mentioning, like one can construct like in 2D, for example, some sort of trial solution, like model solution. So you take the half space, right, or the half plane, right, and you solve this problem, okay? So what you can show is that this solution U, okay, which is basically the real part of z to the power 2/2, right, 2 alpha, solves this problem, right? So it gives you exactly what I was saying, that away from the 0 set, you grow like a power alpha. Okay, so it gives you like at the same, it gives you like a global profile, right, of this equation. Okay, so years ago, in the beginning of 2000 or so, no, sorry, 2010, I proved the following. We proved the following theorem with Caffarelli and Rockjoff. So let's take like a minimizer of this functional, okay, which is H1 with the suitable weight. Okay. Well, by the way, since alpha is between 0 and 1, okay, so I'm considering like the case where the power of the Laplacian has maximum principle. Beta is -1 and 1. In particular, this weight is A2. Okay, it's locally L1. Its inverse is locally L1, and it satisfies this estimate. Okay, so the average, these two averages are uniformly bounded in R. So we prove like the following: if you take an even minimizer, okay, of this functional in B1, so now B1 like is a, since you take an even minimizer, you have reflected, right, evenly with respect to the hyperplane. So your B1 is bored in Rn+1, right? Then you can prove that indeed the optimal regularity is C alpha, okay? You are non-degenerate in the sense that you grow like the right power of distance to the free boundary, if f of u is the free boundary. You have an interior corkscrew condition, okay, which is like very important. You can prove also that you have positive density, right? So you rule out cusps of the zero phase. And blow up are minimizers, okay? And also you can at every point on the free boundary where you have a measure theoretic normal, because at the moment I don't know any kind of regularity of the free boundary. So this free boundary condition that I wrote here is satisfied. Okay. Okay. So, of course, like I mean, even like as it's well known for free boundary, you can use always what is called like a high activation limit, in the sense that you can always approximate your problem. I mean, you can, in some cases, you can approximate your problem where you take beta of epsilon by something which is not a free boundary problem, right? And beta epsilon is an approximation of the Dirac mass. And obtaining like uniform estimate in epsilon, right? You can pass to the limit and construct this way a solution to the free boundary problem, okay? So, for example, one of the first paper dealing with that in any dimension is a paper by Berestiki, Caffarelli, and Janberg. Okay, this is a way to construct for the case alpha equal to 1, okay, so for the one phase problem. So it is a way to construct a solution to your free boundary problem, okay? So if you do that for the fractional Laplacian, we did it with Archak Petrosen and went with Xi, and you manage, at least in some cases, to recover a solution of this problem, okay, that I mentioned here. Okay. So now, okay, so now basically this result that I stated before, well, tells us that, okay, we have optimal regularity. We know what is a non-degeneracy. Well, we know that the solution, okay, so the minimizer, by solution here I mean a minimizer, is non-degenerate. We have some kind of measured theoretic properties of the free boundary. It has positive density, it has an interior corkscrew condition, and there is like the right behavior at the free boundary whenever you have the normal in the de Giorgi sense, for instance. Well, the question is, what is the regularity that one can expect of the free boundary, right? So in other words, in this paper with Caffarelli and Raujo, we prove that in 2D, when I say 2D, I mean like n is equal to 2. So basically the half space is three-dimensional. We managed to prove that the free boundary, the regular points of the free boundary are like C1, okay? But somehow like this is not satisfactory at the moment. Well, because first it was working only in 2 dimensions, and second, we got just C1. Okay, we would like to have more regularity to be able to at least like do a bootstrap argument to have like a full regularity of the free boundary, at least at the flat point. So the problem is that so let me kind of digress a little bit about like and say that tell you what is known for the Al-Caffarelli problem. So for the Al-Caffarelli problem, we know that by a series of results that the free boundary has finite perimeter, okay, and can be split into these two sets, right? A set of regular points and a set of singular points, okay? And you have like kind of a priori bounds on the other dimension of this set. And the question is, can you rule out singular points in at least in low dimension? Okay, so is the free boundary, okay, so which is like the set formally where the topological boundary where of the positivity part, right? The positivity phase is actually fully smooth, okay? So it doesn't have singular points at all. So in dimension 2, it's known, okay? This is in the original paper of Alt and Caffarelli. Then in dimension 3, it's been like proved by Caffarelli, Jerison, and Koenig. But the proof is very much 3D. Then, years after, in dimension 4, it's been proved by Jerison and Savin, where that there is no singular set for the free boundary, okay? So the free boundary is completely. And in dimension 7, there is an extremely nice paper of De Silva and Jerison, where they construct like a singular minimizer. A minimizer having like a singular. So basically, in the case of Al-Caffarelli, it's already open to a full regularity of the free boundary, which is expected, okay, well, somehow, between in dimension 5 and 6. Okay, why is 7 popping up? 7 is popping up because of these analogies that I was alluding before for this minimal surface theory and the existence of the Simon's cone. There is a strong analogy somehow between Al-Caffarelli, the one-phase problem, and minimal surfaces. And what we can expect, and this has been verified in many instances, that techniques developed and results developed in the context of free boundary, in the context of minimal surface theory, codimension 1 minimal surface theory, was is working, well, kind of is working in the case of one phase. Okay, so already the Al-Caffarelli problem, okay, not even with coefficients, it's conjectured that the regularity has no, the free boundary has no singular point in dimension 5 and 6, but this is, I mean, this is widely open. Actually, like the proof of Jerison and Savin, or even the proof of Caffarelli, Jerison and Koenig are not working in dimension 5 and 6, at least like kind of straightforward. Okay. So already before trying to get like such a strong result as a full regularity of the free boundary with Engelstein, Kauranen, Prats, and Sakelaris, we looked at what is, the general regularity that one could expect for the free boundary in the case of the thin one-phase problem. Okay. So if we take, like, once again, a non-negative even local minimizer of my functional, and here I still did not by f of u like the boundary, so the free boundary, okay, boundary of the positivity set, okay, inside on the hyperplane, right? Then it's a set of finite, locally finite perimeter, okay, as a subset of Rn cross 0. And you have also a partial regularity result, okay, so you can split it. You can split the free boundary as disjunct union of an open set, and for which, like, locally at every point, you can write the free boundary as a C1 gamma graph. And the singular set that sigma of u is of outdoor dimension n minus 3. Okay, so by the way, I mean like n minus 3 is a very bad, between quotes, dimension, because by analogy, at least for some range of beta with the Al-Caffarelli problem, one should expect that the Hausdorff dimension of the singular set is much better, because well, of course, it tells us that in dimension 2 there is no singular set. In dimension 3 it's discrete, but already for Al-Caffarelli, so for my alpha here close to 1, okay, if you think about it like formally, in dimension 3 I don't even have like isolated singularities, right? So, but the thing is that at the moment it's still open. Okay. So somehow, so this theorem, I mean, leaves open two kinds of problems. First, can I go from C1 gamma for the regular part of the free boundary to C infinity? So this is not clear, because so for the case of beta equal to 0, okay, so alpha equal to 1/2, it's been proved by De Silva and Savin. It's not clear because the problem is intrinsically non-local, okay? So in particular, it's quite involved to implement the Hodograph transform, which is the original proof, for instance, to prove higher regularity. And because also like C1 gamma is not enough to kind of use like some versions of Schauder, if you want, estimates and Hodograph transform to deal with this problem, which is non-local in nature. It's not because like you wrote it as a local problem, right? As a thin one phase that, I mean, it becomes a local problem, okay? I have infinite support, right, inside, okay? Because I'm just penalizing you, I mean, the volume of the positivity phase on the hyperplane, right? So it's not at all like an easy matter to go from C1 gamma to C infinity, though it kind of, one can conjecture. And of course, like as I was mentioning, at least for some ranges of alpha, right, particularly when alpha is close enough to 1, right, you could expect that the Hausdorff dimension of the singular set should be n minus, well, at least n minus 5, right? Because like for the Al-Caffarelli model, we know that in dimension n minus 6, sorry. For the Al-Caffarelli model, we know that in dimension 5 and 6 there is no. In dimension 4 and 5, sorry, there is, and 3, there is no singularity of the free boundary. Okay? Is it clear up to now, or? Okay.
Okay, Yannick.
Okay. So there are several tools that one would like to use to prove this theorem. Actually, I will state later a theorem where I give more information on the singular set. Okay. So years ago with Ovidio and Daniela, we proved the following. So this is what I will call like a epsilon regularity result, okay? Or flatness implies C1 alpha. So if you have the free boundary, okay, which is stuck properly between two planes, okay, so I have, considering flat points of the free boundary. Then in a ball of radius 1, in a smaller ball, I have my free boundary is C1 gamma. So this is like in the statement of my previous result. This is this item where, okay, the regular part. Okay. So this part we proved it in with Daniela and Ovidio years ago. Okay, and in the case beta equal to 0, Daniela and Ovidio proved it before, but the proof is very much in the same spirit. Okay, so actually the thing is that what we were kind of most motivated with Max Engelstein and Apo, Marty, and Georgios was to kind of understand what is like a finer structure of the singular set. Okay, because now we know at least that the regular set is a C1 gamma graph. Okay, so somehow like up to proving to going to higher order regularity, which is not trivial, but at least we know that this is like a C1 alpha graph. So the motivation for this theorem was kind of a very nice recent result of Engelstein and Edelin, where they proved that in the Al-Caffarelli functional, so the original one, the singular set is actually a rectifiable set. And even better, they have volume estimates. So actually that this type of, as far as I know, it was not known in general dimension that the singular set for Al-Caffarelli was rectifiable. And how do you get, but actually one gets better, one gets like volume estimates on the strata, and this is kind of reminiscent of a very, very nice theory that Neighbor and Valtorta developed recently to study, to have like some sort of to have quantitative stratification of singular set in a lot of geometric problems. Okay. And the thing is that is Edelin and Engelstein figured that this volume estimate that Neighbor and Valtorta got, like for the singular set of harmonic maps, and in a lot of originally actually it's Chigger and Neighbor to solve the codimension 4 conjecture. Edelin and Engelstein figured that it could be applied to Al-Caffarelli, and this is another instance where you see that Al-Caffarelli is really, I mean, somehow like it's a very geometric problem, because like the Neighbor and Valtorta theory was really designed originally somehow, but it has a much wider application to geometry variational problems. So the thing is that what are the tools to apply the theory of quantitative rectifiability of Neighbor and Valtorta is actually relying on a bunch of tools that your problem needs to enjoy, okay? And one of them is the epsilon regularity, so flatness implies C1 alpha. And the other one is a monotonicity formula. So there are many monotonicity formulas for this type of problem, right? The one which is useful for us is the Weiss type monotonicity formula, which writes in this case like this, right? So this density, so you take the functional, you normalize it, and you retrieve an average on the ball, okay? So it looks like rearranging the Angren the terms in the Amgren monotonicity formula, is a non-decreasing, so it's well defined, it's non-decreasing, and the thing is that you can compute explicitly the difference at two different radii, right? And it gives you exactly that, you see, like you recognize, like that u, it's going to be 0 if and only if u is non homogeneous of degree alpha, right? Like the direct computation of Weiss. So it was proved in this case of the weighted one-phase problem, or two-phase, like in the by Mark Allen. Okay. So the thing is that a direct consequence of this monotonicity is that if you take a rescaling, because of course, like you want to, if you want to study the regularity of the free boundary, an important, an important aspect is to understand what are the entire solutions, right? So basically, you want to blow up the picture, right? So because of this monotonicity formula, one can prove that the island-wise density, right, is well defined, right, in the limit r going to 0. And for any sequence of rescalings UK, right, there is a subsequence which is going to converge to a globally defined minimizer, okay, and which has to be homogeneous of degree alpha. Okay, this is exactly what Weiss tells me in this case. Okay. So blow-up limits are cones. Okay, blow-up limits are cones. So what would be like the important aspect to study? Well, now, if one wants to rule out singular points, one need to understand what are those cones. Okay, it's going to be like is there really a cone, or it's only a half space, and so on. So recently, Fernandez Real and Rosoton started investigating this the case of trying to understand, trying to classify the blow-up cones, right? And trying to understand what are exactly like the possible limiting configurations that one can have for this type of problem, okay? But once again, this problem is not at all easy classifying the cones, and this is mainly due to the non-locality of the problem. Because so let me give you, like, for example, another instance of the non-locality, which actually creates a lot of trouble at the analytic level. Is that if you take Al-Caffarelli, okay, if you take Al-Caffarelli, okay, you can prove that the Laplacian of the solution will be a measure along the free boundary. Okay, so it's going to be like a concentrated, right, along the free boundary. Well, it happens that for the thin one phase, even for beta equal to 0, right, it's not concentrated. The delta 1/2, okay? Or in other words, like the Neumann derivative is not concentrating on the free boundary. The fact that the Laplacian is a measure on the free boundary, supported on the free boundary, gives automatically a lot of properties of the free boundary, at least measure theoretic properties of the free boundary, finite perimeter. Here, this is not the case. You don't have somehow like the mass, you see the mass spreading all over, right? So one can still prove that one has like positive density and finite perimeter, as I stated here, right? But one needs to go in other ways to prove it. Why do I say that? Well, I say that because this is like what I wanted to discuss. I say that because like one could think about like recently, David Feneuil and, oh, sorry, I misspelled Feneuil, and Maiboroda developed like a theory of harmonic measure in higher codimension. So your harmonic measure was designed in a complex analysis, like out of the Laplacian to understand the properties of the set somehow. So by means of its boundary, I mean, through understanding the Dirichlet problem somehow for the Laplacian inside. The thing is that, of course, like because of the Laplacian and for capacity somehow reasons, you can see only codimension one set, right? So what do you need? Which type of operator would allow you to see higher codimensional sets? So for example, a curve in the 3 space, right? Well, these operators were exactly of this form. Divergence of omega gradient u, where omega is exactly distance to my set. So here, the problem of the free boundary problem is also a problem of this type, because my free boundary is a boundary in a codimension 1 set, right? So it's codimension 2, right? So I am, but my equation somehow is in seeing a Laplacian, right, for beta equal to 0. So that's why this is another feature of the problem, is that if one wants to investigate free boundary, fine properties of the free boundary, one needs to understand somehow much better. But David Feneuil and Maiboroda released a lot of papers, like recently. What is like this higher codimension harmonic measure? Okay, and in particular, it's quite important if you want to have endpoint cases. So like in the series of work developed by Koenig and Toron. So these are somehow like if one has one thinks about like trying to understand the free boundary properties out of kind of more harmonic analysis type techniques, right? Or GMT techniques. I mean, one needs really to understand higher codimensional harmonic measure. Well, this is one way to possible understand it, and this fact creates a lot of difficulties. Okay, so I listed here several open problems. Let me mention that, of course, like one could hope that you have, well, one could think that at least in some range of alphas or beta, if you want, you have full regularity in 3D. Well, at the moment, we just have like, we know that we have like point singularities by our result, but we cannot rule out these points. And why is it so? Well, it's so because somehow a major tool in the case of, for example, Jerison, Savin result, or Caffarelli, Jerison, and Kenny, is to understand what are the block cones, right? And the thing is that the analogy for this problem, so I mentioned that earlier that there is a very strong analogy between minimal surfaces and Alcafarelli problem. Well, this is no longer the case, at least like the analogy is not clear. For this scene one phase problem, actually when alpha is bigger to 1/2, you could expect that in this case, you are closer and closer to Alcafarelli. But for alpha less than 1/2, you fall into an object which is like called non-local minimal surfaces, for which actually it's very hard to understand what are the cones also. So the analogy with minimal surfaces carries over at least for some range, but the problem is that like because of the intrinsic non-locality of the problem, it's very hard to go to kind of understand what are the blow-up limits, and this is like somehow the crucial point. So I mentioned also like a last item. This is like because like this problem actually, like as I was mentioning, like a more natural way to attack this problem because of the fact that we are in higher codimension is to use GMT tools instead of really PD tools per se. And it happened that for certain powers, one can have like kind of very easily a strong compactness of minimizers almost for free by using like a Marstrand theorem, which is like a preliminary version of the rectifiability theorem of price. So so let me finish by saying that, well, at the moment there are many open questions somehow, and I think that somehow like the most in particular from the point of view of application, somehow the most interest from my point of view, one of the most challenging would be like to study the regularity of the free boundary. So I think I'm going to stop here. Thank you very much.